In this example, let's say we have a stick or a rod that's 6 meters long and has a mass of 10 kilograms. And also 2 3-kilogram bugs, really big bugs, standing on the center. And the stick is spinning at 10 rotations per second around its own center. And let's say it's spinning in such a way that the angular momentum is, let's say, downwards. So we've got a downwards angular momentum in the sense of the right-hand rule axis. But the bugs don't like the fact that it's spinning so fast and they'd like it to slow down. What could the bugs do in this context to make this rod slow down its rotation?
They could move farther away from the center.
Yeah, if they change their position, if they move further outwards from the center, why would that cause the rod to slow its angular rotation? Or slow its rotational speed?
It's like because the mass is spreading out, and so I think it's is it R increases, or what's the variable?
Yeah, we are increasing R, because R in the sense of the distance from the center. We're making the mass further away, some of the mass further away from the center. And how does that play into the angular momentum? Right, we're increasing the moment of inertia by making some of the mass further from the center. And so that means we're decreasing the angular velocity. If we just treat this for a moment as just one big object, the angular momentum total, the angular momentum of the whole thing, equals moment of inertia of the whole thing times the angular velocity. If we move some of the mass further from the center, we are increasing moment of inertia. But the total angular momentum shouldn't change because this is a closed system. So we should expect the angular velocity to decrease. You're going to slow down the system's rotation by making some of the mass further away from the center. Exact same principle as figure skaters slowing or speeding up spin in mid-leap by pulling arms in, or slowing down spin by putting arms out. Because we should only expect the total angular momentum to change under what circumstances? What's the only thing that can change L total? Yeah, a torque, specifically a torque from somewhere else. While the bugs are walking, they're actually applying torque to the rod, and the rod is applying torque to them by the contact of their feet. But they're not actually experiencing any torque from anywhere else. There's no external torque going on here, only torque between the bugs and the rod. So the total angular momentum is only changed by an external torque. Torque from some other object that's not part of the system, and we're assuming these are only interacting with each other. Presumably this is just floating in space, or it's in free fall or something. So we can assume conservation of total angular momentum, and that means we can use everything we've seen about conservation of translational momentum. We're just applying it to angular momentum instead. In fact, we could even deal with this using a momentum chart. We could set up a chart for initial angular momentum, change in angular momentum, and final angular momentum. And the objects, of course, are going to be the rod itself, bug 1 and bug 2. And then, of course, we'll want to look at total as well. So to calculate all of these, how do we find all of these angular momentums are just moment of inertia times angular velocity? We know the starting angular velocity. How do we define moment of inertia?
Is it mr squared?
Yeah, at least we can use that for what sort of objects?
where mass is consistent around the object, or is something like that?
Specifically a consistent radius. If the entire mass is just one single radius, one single distance from the pivot point, then we can use mr squared. Is that true for any of the objects in this system? And why not the bugs? What's the problem with the bugs here? They are moving away from the center as time passes, but keep in mind that initial and final are just looking at one single instant in time each. So at the initial situation, can we say the bugs are a specific distance from the center? Where are the bugs at the beginning? They're at the center, right? So what's the distance from the center to the bug at the beginning? 0. And that is a specific distance. That distance is going to change as time passes, but at this instant, R does have just one specific value for the bugs, and that specific value is 0. And then at the final situation, if we take a look at final, we're going to have the same rod still spinning around the same axis, but presumably more slowly. And in the final situation, where are the bugs? Six meters apart from each other. But we should be measuring these distances relative to what? Yeah, from the center. So we say exactly 3 meters from the center. So based on the axis of rotation, we would say that in the final situation, this bug is R equals 3 meters from the center, and this bug is also R equals 3 meters from the center. And that is for each bug, just one specific value. Even if there were different locations, we could say each bug at each instant in time has one specific value of R. So we actually can use this formula for the bugs because they act like just a single point. Even though that point is moving, if we take a look at any single instant in time, like at this final situation, this bug is just at 3 meters. It's not smeared out over several locations. It's just at 3 meters. Likewise, at the beginning, this bug is just at 0 meters. It's not big enough to take up multiple locations. We can treat it as just a single point. And that's really the important thing about this formula. This formula works for a point mass. Point mass in the sense of a mass that we can treat as acting like a single point in space. Its own size is small compared to the other distances involved. Like maybe some of the bug's mass is at like 2.99 meters and some of it is 3.01 meters, but we can treat it as being all at 3 meters. It's not big enough for that to matter. Also, you can use this if you have an object where all the mass is the same distance from the center, or like a ring or a wheel. In an object shaped like a ring, like a bicycle tire would be a good example of this, you can treat all of the mass as being the same distance from the center. So even though the mass is not one single point, all the mass is the same distance from the center as all the other mass. So you can just multiply the total mass times that one distance squared. In this case, the rod itself takes up a wide variety of locations. So we can't use mr squared for the rod, but we can use mr squared for the bug. It's just that the bug's R is changing as time passes. Any questions on that so far?
Wait, yeah, sorry, just to clarify, you're saying we can't use mr squared on the rod, but we can on the bugs?
Yeah, we can use mr squared on the bugs because at any instant in time, each bug takes up only one location in space. Like at this time, this bug's R is 3 meters and just 3 meters. That's the only R value that bug has at that time. And of course, R is changing as time passes, but that's not what this formula is about. This formula is about at a single instant in time. But we can't use this for the bug because, or sorry, for the rod. We cannot use this for the rod because the rod is not one single location. The rod's mass takes up a wide variety of locations, all over that distance. Any questions on that so far?
So how would you calculate I for the rod?
For the rod, either we could split it up into little pieces. If we take a look at, like if you imagine splitting this rod up into a bunch of small pieces, you could treat each one of those pieces as acting like a point mass. And for each one of those pieces, take the tiny bit of mass times the distance from the center squared, plus this tiny bit of mass times this distance from the center squared, plus this tiny bit of mass times this distance from the center squared, and so on, and add up all those tiny pieces. But mathematically, what's the best tool we have for adding up lots of tiny pieces?
It's like an integral.
Right, this just becomes an integral. To find the moment of inertia of a more complicated shape, if it's not just a single point mass, what you do is you take tiny bit of mass, usually written as dm, times r squared, and then use an integral to add all those tiny bits together. And actually evaluating this integral can be tricky because r is not written in terms of m. So usually what you want to do is rewrite dm in terms of some distance variable. Usually using the idea of linear density. Linear density, usually written as lambda, is mass per unit of length. So if it's uniform density, you could just say total mass divided by total length. And you could then also say lambda equals a tiny bit of mass times a tiny bit of length. Tiny bit of mass dm divided by tiny bit of length dr. And if you solve that for dm, what do you get?
Lambda dr.
Right, which means we can make that substitution. dm could be replaced with lambda times dr. Lambda just being the linear density of the whole thing, which would be the total mass divided by the total length. In fact, let's fill that in. Total mass divided by total length. So integral of tiny bit of mass times r squared. Integral to add them all up. And the tiny bit of mass is just the tiny bit of length modified by mass over length. If you look at this in terms of units of measurement, the units cancel out, the meters cancel out because dr is a tiny bit of meters, L is a larger amount of meters. Meters and meters cancel out, we're left with kilograms times meters squared. So this integral should tell us the moment of inertia of this rod. And of course, we'll also need to figure out the limits of integration. Because if we're talking about r goes from where to where here?
It's like 0 to the whatever the final length is. Is that
Well,
like
0, what would r equals, or what location would be r equals 0?
the center?
The center. So if we go from 0 to length, we're going from 0 out to 6 meters, but that overshoots the end of the rod. So instead, we should be going from 0 to where? 0 to 3, right? If we treat this as r equals 0, the end of the rod would be r equals 3. But that only covers half the rod. There are a couple of ways we could address this. One way is to calculate it from 0 to 3 and then double the result. Or alternatively, we could cover the whole rod by starting over here, treating this as -3 and evaluating from -3 to 3. So either way will work. They'll both get the same result. Let's try that out real quick. If we just integrate from, in this case, from 0 to half the length of the rod, from 0 to L over 2, that is from 0 out to the edge, but then double it because we've got 2 copies of that half rod. And we're integrating r squared times mass over length times dr. Because mass over length times dr is the same as dm, a tiny bit of mass. So we really do still have here tiny bit of mass times radius squared, the formula for a point mass. but then we're using an integral to add together all those little pieces. And how would we evaluate an integral like this? Is there anything we can pull out of that integral before we try evaluating it?
Is ML a constant?
Yeah, M and L are constants, because this is just the total mass of the rod, in this case, 10 kilograms, and the total length of the rod, in this case, 6 meters. So that can be pulled out of the integral. So we just get 2 times M over L times integral from 0 to L over 2 of R squared dr. And what's the integral of R squared?
Should be 1/3 R cubed.
Yeah, exactly. 1/3 R cubed. So that whole integral just becomes 1/3 times R cubed. And that's evaluated from 0 to L over 2. So if we plug in L over 2, what do you get if you cube L over 2?
It's 1/8 L cubed.
Yeah. So L over 2 cubed becomes L cubed over 8. And then you plug in 0, you cube 0, you just get 0. So that's just L cubed over 8 minus 0. So this should give us the moment of inertia for that rod. And we can also simplify this a bit. What's going to cancel out or reduce here?
The L's can be simplified to L squared.
Yeah, one of those L's cancel out, so we're left with just L squared. Any of the numbers reduce?
Yeah, 2/24 can be 1/12.
Yeah. So we're going to end up with, yeah, just 1/12. So we end up with mass times length squared over 12. So that should be the formula for moment of inertia for a rod, specifically a rod spinning around its own center. And of course, we don't need to run through this integral every single time. From now on, anytime we're dealing with a rod spinning around its own center, we can assume that its moment of inertia is 1/12 times mass times length squared. And in general, moment of inertia formulas tend to be some fraction times the mass times the distance squared. And of course, setting up the integral for every single shape you encounter can be pretty tedious. But fortunately, we're not the only people to have ever tried calculating the moment of inertia of a rod spinning around its own center. So typically what you would do is just look up a formula for that moment of inertia of that shape. If you have a formula sheet kind of like this, just a list of shapes and the moment of inertia associated with them. For instance, this rod spinning around its own center, moment of inertia is 1/12 times mass times length squared. That's exactly what we just found. So you can look these up on a data table of shapes. If you just look up, did they give you a formula sheet for these moment of inertia of various shapes?
We talked about it in last week's lecture.
Okay. And you can also look that up online. If you just look up moment of inertia of shape, whatever shape you're looking for, you can probably find the data table. In this case, though, the rod is 1/12 ml squared for its moment of inertia. That's not going to change because the mass is not changing its mass and also not changing its length. It's just staying the same length, spinning around its center forever. So we can actually calculate that. In this case, if we just plug in these values, 6 meters for L, square that, we get 36, times 10 kilograms is 360, divided by 12 would be 30. And the units there, as usual, would be kilograms times meters squared. So it looks like that is our moment of inertia for the rod. Moment of inertia for the rod is 30 kilogram meters squared. Any questions on that so far?
Wait, sorry, real quick. So we got 30 because L is 6?
Yeah,
And-
L is the total length of the rod.
Oh, and then 10. Okay, got it. Okay, thank you.
So 6 meters as the length, square that, we get 36. But 1/12 of 36 is 3, times 10 kilograms for the mass, and we get 30. So 30 kilogram meters squared should be the moment of inertia of the rod. So the moment of inertia of this rod is 30. And we can use that to find the angular momentum, because how do we calculate angular momentum? That's just going to be the moment of inertia times what? Yeah, times omega, the angular velocity. And we have the initial angular velocity, 10 rotations per second. So for the rod, the initial angular momentum is going to be I times omega, moment of inertia times angular velocity. And just like translational momentum, that's just how fast it's moving, or in this case, spinning, times how difficult it is to change that motion. Moment of inertia just being the level of difficulty to change the angular motion. So I times omega would be 30 times 10 equals 300. And that's going to be downwards because that's the direction of the rotation. That is the direction it's rotating around. So 300 downwards would be the angular momentum here of the rod initially. And as for units, we've got kilogram meters squared times rotations per second. Usually it's a good idea to convert all angular stuff into radians. So for instance, one rotation would be how many radians? Two pi. So we could change 10 rotations per second into 2 pi times 10, or 20 pi radians per second. However, if all you're doing is comparing angular momentums to other angular momentums, or comparing angular speeds to other angular speeds, if you're not really going to be doing any changes like finding torque or anything like that, if all you're doing is comparing a value to other values of the same type, then it doesn't really matter what units they're in, as long as they're the same units of measurement. So in this case, I would just leave this as 10 rotations per second. But if you're going to be comparing it to anything else other than just an angle, anything other than just angular speed, angular acceleration, angular momentum, then I would recommend converting that to radians instead. So we know the angular momentum of the rod at the beginning, and this whole thing is going to be measured in kilogram meters squared rotations per second as the units of measurement of the whole thing. Do we know anything about the final angular momentum of the rod? Do we know how fast it's spinning in the final situation? The units, kilogram, let me make that a little bigger. The units for I, moment of inertia, would be, in this case, kilograms times meters squared times rotations per second. And rotations is just what we're currently using to describe angle. 10 rotations per second. That's how fast it's spinning. But it doesn't have to be rotations. It could also be measured in radians per second or degrees per second. So you could have kilogram meters squared times radians per second, or kilogram meters squared times degrees per second. But keep in mind, radians is technically unitless. So this should just be in kilogram meters squared per second. But in this case, we're using rotations instead of radians. So we've got the initial angular momentum. Do we know anything about the final situation of the rod? Do we know how fast it's spinning at the end? It comes to a complete stop. We know that the bugs moving outwards is going to make it slow down. Will that be able to make it come to a complete stop? No, we can't make it come to a complete stop because we still have to preserve I times omega. And so it's still going to be spinning. It's just going to be spinning more slowly. So we don't know its final angular speed. We don't know how fast it's spinning at the end. But we at least know that it's going to have the same angular momentum, because for the rod, the mass is not changing and the length of the rod is not changing. So the final moment of inertia for the rod is still 30 kilogram meters squared. So this is still going to be 30 times, and then we don't know the final angular speed. So 30 times some unknown final angular speed. presumably still in the downward direction, because it's not going to change direction. It's just going to change how fast it's spinning. What about for the bugs? At the very beginning, what's the moment of inertia of the bugs? Should be 0, right? And why is that? If we go back to the formula for moment of inertia for a point mass, yeah, the radius is 0. If the bugs are at the center, they're at the pivot point. So r is 0, because all the distances are measured from that pivot point. So that means at the beginning, the bugs have 0 moment of inertia. We multiply 0 times omega initial, and we still get 0. So at the beginning, the bugs have 0 angular momentum. Add these together, 300 downwards plus 0 plus 0, we get 300 downwards. And how much change should we expect to the total angular momentum? Yeah, should be no change at all. Add those up, 300 downwards plus a 0 vector is still 300 downwards. So that means these 3 values have to add up to 300 downwards. But if the bugs have moved out to the end of the stick, their moment of inertia is no longer 0. So we're going to have to find their moment of inertia finally. So the final moment of inertia for each bug is going to be mass times radius squared. For each bug, the mass is 3 kilograms. And what's the final radius for the bug? Right, because it moves out to the end, which is 3 meters away from the center. So 3 meters squared. 3 squared would be 9, times 3 again would be 27 kilogram meters squared. So that's the final moment of inertia for each bug. So each bug is going to have a final angular momentum of 27 times some unknown angular velocity. Presumably also downwards, because everything's spinning together. Nothing is starting to spin in the other direction. It's all spinning the same way. Just to do, if we were assuming from the start that the rod was spinning in this direction, which is a downwards angular momentum. So the downwards is talking about the axis that it's spinning around. If it's spinning like this, that's spinning around a downwards axis based on the right-hand rule. On the other hand, if it was spinning like this, that would be an upwards axis. So the direction of angular velocity, angular momentum, all this angular stuff is really just talking about the axis it's rotating around. And I just chose downwards arbitrarily, assuming it's rotating like this to start with. However, since the bugs are attached to the rod, what do we know about all these final angular speeds? They're all the same, right? Just like if you've got 2 objects moving and they stick together, their final speed final translational speed has to be the same. Likewise, if you've got several things attached to each other and they're all rotating together, their angular speed has to be the same. So we can assume that omega final is the same for all of these. So we just got 30 omega final plus 27 omega final plus 27 omega final equals 300. So that's our equation to solve. We can now say confidently that 30 omega final plus 27 omega final plus another 27 omega final has to equal 300. And we could call that negative 300 if we wanted to treat it as a y component, but we know these are all going to be downwards anyway, so let's just focus on magnitude. Combine like terms here because they all have the same omega final. 30 plus 27 plus 27 should be 84 omega final. And then what's our last step here? Yeah, if we just divide by 84, that should tell us the final angular velocity. So 300 divided by 84. is about 3.6. So that would be the final angular velocity of the whole system. And that would still be in rotations per second, because the whole thing, the 300 was in kilogram meters squared rotations per second. We're dividing by 84 kilogram meters squared. So we're left with 3.6 rotations per second. So that means the whole system has slowed down from 10 rotations per second to about 3 2/3 rotations per second. It's slowed down almost all the way to 1/3 of the original speed, because we are drastically increasing the total moment of inertia. In fact, we went from 30 to 84. We've almost tripled the moment of inertia. So we cut almost to 1/3 the angular speed of the whole system. Any questions on that so far? And then if we wanted to, we could also fill in the delta column. Now that we actually know 3.6, we could fill in 30 times 3.6, 27 times 3.6, and another copy of 27 times 3.6. 108 plus 97 plus 97 is 302. I rounded off a little bit so it doesn't exactly add up, but close enough. But we can now figure out the changes. For instance, from 300 downwards to 108 downwards, what's the change there? Negative 192, which really means 192 in which direction? Right, upwards. Because we changed from a lot downwards to a little bit downwards. The change is upwards. And likewise, 97 downwards versus 0, what's the change there? Yeah, 97 downwards, because we're going from 0 to 97 downwards. Same thing here, 97 downwards minus 0, final minus initial is still going to be 97 downwards. Because we're starting at 0 and we're changing to 97 downwards. So that's a change in the downwards direction. You could also think of that as final minus initial. Subtracting 0 doesn't change anything. But then we compare these, 192 upwards plus 97 and 97, that's a total of 194 downwards. They don't quite cancel out because we rounded off a little bit, but close enough that we can just treat that as a rounding error. So these should add up to 0 or close enough to 0 to be a rounding error, because the rod is gaining upwards angular momentum as a result of the bugs, and the bugs are gaining downwards angular momentum as a result of the rod. They're interacting with each other. They're not creating anything new. They're not creating any new angular momentum. They're just exchanging angular momentum that they already have. So the total angular momentum does not change. We're just changing how it's distributed. Any other questions on that so far? And there was some mention of Newton's laws earlier. Any questions on Newton's laws or how they work? Just a quick review of Newton's laws. So 3 laws. When the rod slows down, the rod is still spinning in the downwards direction. It hasn't changed the direction of spin, because its initial angular velocity is downwards, its final angular velocity is still downwards, but it's changing in the upwards direction in the sense that it's getting slower. So I would say the direction of the angular acceleration is upwards. So we could say alpha is upwards. The initial angular velocity is downwards. The final angular velocity is also downwards, but smaller. So it has changed in the upwards direction. That means the angular acceleration is upwards. And in general, if the angular velocity and the angular acceleration are in different directions, that means the object is getting slower, specifically if they're in opposite directions. Just like if you've got an object moving in one direction, but the acceleration is in the other direction, the object is getting slower. And this also ties into Newton's laws as well. For example, what is Newton's first law? If there's no force at all, what does that tell you? Right, no force means no acceleration. No, and I should say no net force on the object. And this goes in both directions. If you have no net force on the object, then the object is not accelerating. And if the object is not accelerating, then you know there's no net force on the object. Maybe there are some forces, but they all cancel out. And note that no acceleration might mean the object is staying still, or might mean that it's moving at a constant velocity, not changing its speed and not changing the direction of travel, just moving in a straight line at a constant speed. That would be no acceleration. You can also kind of apply this to rotational motion. You just have to substitute force for torque. The rotational version would be no net torque means no rotational acceleration. But that's not always true. For example, in this case, we were able to change the angular velocity. We caused rotational acceleration. We changed the angular velocity without any external torque. And how were we able to do that? How are we able to change how fast this rod rotated without even needing any external torque? Yeah, we move the positions of some of the maps, in this case, the bugs. So that's changing the moment of inertia. That means that this formula, this idea of no net torque means no angular acceleration, that falls apart if the moment of inertia is changing. So we can really say no net torque equals no angular acceleration if moment of inertia is constant. If the moment of inertia changes, that kind of falls apart. We can, however, still say that no net torque means no change in angular momentum. It's just that the angular speed can change without changing the angular momentum if you mess around with the moment of inertia. Newton's second law gives you a little more detail on what happens if there is a force. Specifically, the total force, or the net force, causes acceleration, and the ratio there is moment of, or the mass. The constant of proportionality there is mass. So if Newton's first law says if there's no net force, then there's no acceleration, and vice versa. Newton's second law describes how net force is related to acceleration if there is a net force going on. And you can use this in many different ways. If you know the force acting on an object, you can divide by mass to find how fast it's accelerating, how fast the velocity is changing. Or if you know the acceleration, you can multiply by mass to figure out what the forces have to add up to. In these statics problems we've been working on, what do we usually assume the forces add up to? If you've got an object just staying still, yeah, the forces have to add up to 0. In a dynamics problem, if the object is moving, and not only moving, but accelerating, because if it's not accelerating, you can still assume no acceleration means no net force, even if it is in motion. But if it's moving and accelerating, like maybe in an elevator that's getting faster and faster, if you know the acceleration, you can multiply by mass, and that tells you what the forces have to add up to, which would in that case not be 0. But it's still useful to know what the forces have to add up to, even if that is not 0. And you can also apply this to rotational situations, that the net torque equals the rotational version of mass, moment of inertia, as the rotational version of acceleration, angular acceleration. And this one, again, only applies if moment of inertia is constant. If the moment of inertia is changing, then that throws things off. We can always say that torque causes a change in angular momentum, that the net torque equals change in angular momentum over change in time. But if moment of inertia happens to be constant, we can be a little more specific. And then the third law is just all about relations between forces in the same system. It's often described as forces, for every force there's an equal and opposite force, or for every action there's an equal and opposite reaction. But it's really talking about the same force viewed from different perspectives. The force from object A on object B is the exact opposite of the force from object B on object A. If I'm leaning on a wall, then I'm applying a force to the wall, and the wall's applying the exact same force to my hand, but in the opposite direction. So Newton's third law is all about pairs of forces from one object to the other and from the other object back to the first object, saying that they're essentially the same force, just viewed in opposite directions. And that also applies to torque. In this case, if you look at what's going on internally, each bug is applying a torque to the rod as it moves. And the rod is applying the same torque back to that bug, but in the opposite direction. If you know how much time this process takes, like if you know it takes 5 seconds for the bugs to reach the end, you could even calculate the average torque by using the idea of impulse. That torque equals change in angular momentum divided by change in time. We know the change in angular momentum. If you divide that by how much time it takes, like let's say we know that this process takes 5 seconds, this change divided by that amount of time tells you how much torque was applied to that object. Why don't the torques cancel out? In the sense of the equal and opposite ones? You wouldn't actually add those together because they're not acting on the same object. When we're talking about net force or net torque, we're talking about all the forces acting on one object, or all the forces acting on, or all the torques acting on one object. So if you look at all the torques on the bug, those don't cancel out. Or if you look at all the torques acting on the rod, those don't cancel out. The only time we'd be adding together torque on the bug plus torque on the rod is if we're treating the whole thing as one big object, in which case those torques would cancel out because they're all internal torques. They're not external torques that change the total momentum. So typically, the only reason you would add together forces or add together torques is if they're all acting on one object. And Newton's third law is all about two different objects, the force from A on B and the force from B on A. So these are not the sort of forces you would typically be adding together. Any other questions on that? All right, then I will see you next time.